Hello. In the past two episodes, we looked at the qualitative and quantitative aspects of chemical changes. Today, let's explore this even further. We will study the relationship between masses and moles of reacting substances. We will show you how to use chemical formulas and equations. These are full of information, so we must know how to interpret them. Finally, we will also try to identify patterns in chemical changes. So stay tuned for an informative and engaging half hour of chemistry in action. For a start, let's try to establish a relation between the masses of the reactions and the masses of the products in a chemical reaction. We will try out several combinations of reactants and make quantitative measurements. Here are lead nitrate and potassium iodide. Lead and some of its compounds are toxic. Therefore, handle and dispose of these very carefully. We also have acetic acid and sodium carbonate. We need a digital balance that reads to 2 decimal places, Erlenmeyer flasks, and some balloons. Watch closely as Jenny De Jesus performs a demonstration. Before weighing the reactants, place the balloon and flask on the balance pan. Adjust the tare to 0 to cancel out their mass. Pour about 100 milliliters of a 0.2 molar solution of potassium iodide into the flask. Transfer about 1.6 grams of lead nitrate into the balloon. You do not have to use these exact quantities, but you do have to follow the procedure described here. To ensure an airtight system, fit the balloon snugly over the flask. To determine the exact total mass of the reactants, place the entire setup on the balance pan. Record the total mass. Watch carefully as Jenny drops the lead nitrate into the potassium iodide solution. This is a colorful reaction. A yellow precipitate forms. This is one indication of a chemical change. Has the total mass changed? No. The total mass remains the same, 102.95 grams. We observe that the total mass remains unchanged or is conserved in this reaction. A single observation does not make a scientific law. To establish a law, more observations should be made. Countless experiments have shown this general pattern. The total mass of the reactants of a chemical reaction is equal to the total mass of the products. This is the law of conservation of mass. Mass is conserved in a chemical change. Will reactions involving gases follow the law of conservation of matter? Let's do another experiment. This time, Jenny will mix 100 milliliters of a 0.4 molar solution of acetic acid and 2 grams of sodium carbonate. Again, you can change these quantities when you do the experiment as long as you know the exact amounts you use. The total mass of reactants is 101.73 grams. On mixing the reactants, the balloon expands since one of the products is a gas. What about the mass of the products? The balance reads 101.62 grams. There seems to be a loss of 0.11 grams. Does this mean the law of conservation of mass is not true for this reaction? The Archimedes principle provides an explanation. When the balloon expands, it displaces a certain amount of air. This air then exerts a buoyant force on the volume of gas inside the balloon, which accounts for the loss in mass. If we calculate the mass of air displaced based on its density and the mass of gas in the balloon, then we can account for the apparent decrease in mass of 0.11 grams. Therefore, the law of conservation of mass still holds. We can use this law to determine mass relationships in a chemical change. Take potassium nitrate. It decomposes into potassium nitrite and oxygen gas when heat is applied. If this is done to 20 grams of potassium nitrate, 16.8 grams of potassium nitrite is obtained. The mass of oxygen gas produced is 3.2 grams, which is a difference between the masses of potassium nitrate and potassium nitrite. This is a chemical equation for the decomposition of potassium nitrate. The symbol delta signifies that heat is applied. The numbers placed before the chemical formula